Ladies and gentlemen, let's welcome Dr. Peyam.
All right. Thanks for watching, and today I will show you how to solve a system that has infinitely many solutions.
Cool.
And the good news is it's still the same technique, Gaussian elimination. So let's solve the following system. Nice marker. Okay. X plus 3y plus z plus t equals 1. Minus 4x minus 9y plus 2z minus t is minus 1. Minus 3y minus 6z minus 3t is minus 3. And y plus 2z plus t equals 1. Oh my God, right? It's a 4x4 system, but don't be scared. You know linear algebra. This might help you. And also, some systems, they look scary, but they're not too scary. You'll see why in a second. So, again, first step is let's forget about the variables. Put everything on a table. So 1, 3, 1, 1, 1. And then minus 4, minus 9, 2, minus 1, minus 1. And then minus, so 0, minus 3, minus 6, minus 3, minus 3, and 0, 1, 2, 1, 1. Now, let's use row reduction. And by the way, the more your row reductions you do, the easier it'll get. So at this point, you can even do 2 at the same time. For example, we would like to eliminate this minus 4. So let's add 4 times the first row to the second row. And also notice here we have a nice cancellation. Everything here is a multiple of minus 3. So let's divide this by minus 3. And then you get the following. 1, 3, 1, 1, 1. And then, so 0, 12 minus 9, it's 3. 4 plus 2, 42, no, it's 6. 4 minus 1 is 3, and then 4 minus 1 is 3, and then 0, 1, 2, 1, 1, sorry, and then 0, 1, 2, 1, 1. Okay. Now, you're excited, I'm sure, to eliminate this. Just one more second, okay, and notice the entries here are also divisible by 3, so let's divide by 3. So 1, 3, 1, 1, 1, and then 0, 1, 2, 1, 1, 0, 1, 2, 1, 1, and then 0, 1, 2, 1, 1.
Wow.
Oh, I know, crazy, huh?
Yeah.
In particular, I know I gave this question a lot of times on the quiz question. 50% of the students were too excited. They're like, oh my God, this is so pretty. Let's eliminate all of them. Careful. Do not eliminate all of them because even though this is redundant information, it's still some piece of information. Namely, y plus 2z plus t equals 1. That's one piece of information. So just be a bit careful. And for example, subtract this row from this row, and subtract this row from this row. Then we get, so 1, 3, 1, 1, 1, 0, 1, 2, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so again, I didn't eliminate all the rows, just 2 of them. And notice this is precisely in row echelon form because there are 2 pivots here, 1 and 1, and everything to the left and below the pivots is 0, and also the last 2 rows are 0. So that's good. But while before you could just get saved with just the row echelon form, here is actually essential to use the reduced row echelon form. So the next step is let's turn this 3 into a 0. And we can do that by subtracting 3 times the second row from the first row. And then we get something like 1, 0, minus 5, minus 2, minus 2. 0, 1, 2, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And this is good. This is indeed in reduced row echelon form because the pivots are 1 and everything above and below the pivots are 0. Okay, how do we interpret this now? So, let me rewrite the matrix. 1, 0, minus 5, minus 2, and minus 2. 0, 1, 2, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Now, here's the thing. So there are two pivots. And in particular, there are two pivots, two columns with pivots on there, and two columns with pivots with no pivots, okay? And why this is important is the columns without pivots, they will correspond to what are called free variables. It's like Free Willy, but with variables. Because let's now go back and write this in terms of x, y, z, t. So in this step is called back substitution. Or back sub, as I like to call it. So this is x minus 5z minus 2t equals minus 2. And then y plus 2z plus t equals 1. And then, well, 0 equals 0 and 0 equals 0. But that's not new information. Now, at this point, you might be stuck. You might be like, well, what can we say about the solutions? But the cool thing is, in this system, there are actually infinitely many solutions. Because notice, for every z and every t, we do get a certain solution x and y. So this is the case where there are infinitely many solutions. How can we write them down? Well, notice, trivially, you can add the equation z equals z and t equals t, which tells you basically x is 5z plus 2t minus 2, y is minus 2z minus t plus 1, z equals z, and t equals t. And again, those are what are called basic variables, so like non-free variables, and those are free variables. Just like in multivariable, you define sort of parametric equations or parametric surfaces. Those parameters, they are what are the free variables. And in particular, once you have that, how can you write the solution? It turns out there's a nice form called a vector form, because you can write the solution as a vector x, which is x, y, z, t, which becomes, if you want, 5z plus 2t minus 2 minus 2z minus t plus 1, and z and t. And you can separate those out, and you get, in fact, z times 5 minus 2, 1, 0, plus t, 2 minus 1, 0, 1, plus the vector minus 2, 1, 0, 0. So that is your solution in vector form. And the nice thing is, based on this description, we get actually a geometric interpretation of the solution. All that this is, it's an object starting at minus 2, 1, 0, 0 in 4 dimensions. But because there are two free variables, they are sort of two parameters, which means the solution is actually a plane in R4. A plane in 4 dimensions, directed, if you want, by the vectors 5 minus 2, 1, 0, 2 minus 1, 0, 1. So this is really cool. In other words, what have we learned today? We've learned how to use Gaussian elimination to find systems with infinitely many solutions. And we wrote the solution in vector form, which gives us a nice geometric description. And so, if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.
Yay!
Woo! Dr. Peyam.
Yeah. What's next though?
Huh?
What's next?
Next, determine when a solution is consistent without even solving it.
Oh, nice. All right, cool.